So there's school lines there.
It's blocking your view.
No? Is anyone there at School of Mines? Can't see anyone. Oh, hey. Can you hear me? Just wave.
I can hear you. Can you hear me?
Yeah, now I can.
Okay.
Yeah, it might be good to switch the camera. But anyway, all right. So right, today the plan, maybe I should say the plan for the week. So the plan is to basically finish chapter 2 today. And then instead of going on to chapter 3, I'm not totally certain of this plan, but I think we can skip and go to, or basically invert the order. We're not going to skip chapter 3 altogether, but return to it after doing chapter 4. And sort of the point in doing that is, I think the most important thing for the semester is to start learning how to use Feynman diagrams. And chapter 4 rather, introduces them, for the most part, without reference to fermions. So we can at least start doing some interactions before we worry about fermions and all that, which we can do in chapter 3. So that'll be the plan, that we'll start with chapter 4 on Wednesday and move beyond just free non-interacting theories, which we're finishing now, at least the simplest version of them, which are scalars. All right, any questions from last time off the bat that we're eating at you between now and then? All right, so...
Actually,
yeah.
I have question regarding the homework 1 that I'm getting a little bit confused. What should be done there?
About
the homework first. I mean the
Homework,
yeah, this
question
one.
number 1. Homework
Question
second,
number-
question number 1 he's talking about, I guess.
Sorry, you're talking about the first homework now.
No.
Second.
The second homework about the first problem.
Yeah.
Yeah, what about it? So this is the one with complex scalar field.
Yeah,
right?
is that to derive something or to prove that the annihilation using the annihilation and creation operator? We have to prove that something.
Well, sorry, let me go back to the, so you're saying you have a question about, this problem with complex scalar fields, right?
Yeah, right. Yeah.
Yeah. So, I mean, right, are you asking about a specific part or in general? I mean, part A is, right, you show the Hamiltonian has a certain form, then you can diagonalize it by introducing creation and annihilation operators. This means, basically solving the eigenvalue problem, right?
Oh.
Was your question about that part, or?
Yeah, that's not.
Yeah. So basically just show,
Just to show.
yeah.
Okay.
Show that this will diagonalize it so that you know basically what the energy eigenstates are. Yeah. And then you actually generalize one step further, right? So like, the way to think about the evolution of complexity, I guess, for scalar fields is that, so we started out with a real scalar field, the simplest possible thing, just 1 degree of freedom. This is now 2 degrees of freedom that are in one unit, one complex scalar field. And then in part D, you generalize it even more, which is you say you have some doublet of complex scalar fields, which, by the way, is what we think that the Higgs in the real world acts as. So it's a relevant problem to do. But here, we just say they come with some label, and you want to just show, given that they have the same mass, that's the only way that they're the same, basically, show that you have these 4 conserved charges. So it's sort of we're going through some progression of complexity, starting with simplest possible thing and moving on to increasingly, higher number of degrees of freedom, but still with spinless objects. Yeah. But anyway, yeah, let me know if there are more questions too about any of the homework. Okay, so right. Now we really want to, well actually sort of today have our first encounter with an object that's very helpful in Feynman diagrams, which is the Feynman propagator. And that came up because we were talking about causality. Right? So one of the things we talked about at the end of last time, right, was the general requirement we want for any two operators, right? For things to be minimally respectful of causality. Their commutator vanish outside the light cone, right? Or x minus y squared less than 0. Right? So this was a restatement of something we knew in non-relativist quantum mechanics. We want these to be totally independent things, so they can't commute. We don't want uncertainty in one measurement to have anything to do with the uncertainty on another one. Right? So that's why we require it. And we want to know does our QFT so far satisfy that? So the first commutator we could look at, which is actually very, very interesting, is the object. So we're going to study this guy who has a name. I don't remember if I introduced him last time. But this guy is called the propagator. He's just defined as the commutator of the field at two different space-time points. So also, right, everything's manifestly Lorentz. I'm working with space-time variables, right? X and Y. I'm not going to write x mu every time, but it's implicit. This is a 4D sig, 4D coordinate, right? I'm not requiring this be at equal times or anything like we were doing when we did our other commutation relations, right? When we introduced phi and chi, the momentum conjugate to phi, right? We required that those be a delta function, a spatial delta function, right? So it was not super obvious that that thing was Lorentz invariant. So by the way, right? How do we come up with some expression for this? We can go farther because we know a nice trick, right? Which is that this guy secretly is just some harmonic oscillator stuff, right? We do a Fourier expansion with annihilation and creation operators. So we know what the left-hand side is. We can calculate it directly, right? So let's just do that. We'll find it looks messy at first, but there's a simplification. So, right, for each one of these, right, I can expand in momentum. And since I'm doing it for two totally different field configurations, I have two different momentum integrals, right? So they're dummy variables. I could pick them to be whatever. I choose P and Q. And I have my funny 1 over square root of 2 EP, which is the thing, because this now is a Lorentz invariant measure. And I have the same thing for Q. 1 over square root of 2 EQ times now the commutator stuff, so I'll have my AP e to the minus IPX plus AP dagger e to the plus APX. And the commutator, the same thing with Q's, right? Big Q minus Y plus big Q dagger e to the I QY. So the reason, right, that the next line is going to be much simpler than that line is because of that commutator. We know the nice commutation relations for A's and Q's, for A's and A daggers rather, right, that they're a delta function. So, you know, secretly we actually only have one integral to worry about because the delta function will enforce that all these terms that we have are either 0 or 1, right? So we'll just get rid of the Q integral. And so inserting our, I'm not going to go through every step, but I mean, this is the scary looking stuff. Now we just insert our momentum, or commutation relations. And we'll get P and Q have to be the same, so this square root will become not a square root. And we'll have e to the minus I p dot x minus y minus e to the I p x minus y. So this is also, by the way, kind of funny, because the way we defined it, the left-hand side, basically, of this equation, which is the delta thing, which is defined as this commutator, right? This is some operators, right? And the right-hand side now is not an operator anymore, right? It's just a number. It's just a value of an integral. So it's become a C number, rather than, or ordinary number, rather than an operator. Okay, so let's talk about actually the other things we know about this too. So, what do we know about delta x minus y? Well, first of all, it's definitely Lorentz invariant. I mean, we could look at this line to convince ourselves, right? So we know for sure that this thing is Lorentz invariant. We made a big deal about that a couple of lectures ago. And now this is p mu dotted into x minus y, and this is mu, right? So there's secretly a mu here and mu's here, right? Fulfills our requirement for making things explicitly Lorentz invariant, right? So we know for sure the one thing we know, that's Lorentz invariant. But what about some of our concerns? I mean, for one, we do want this actually to be non-zero for things inside the electron. Otherwise, I mean, physics is going to be very boring. So let's look at something that's time-like. We know for sure it's non-zero actually for time-like separations. Time-like means very much inside the electron. So we could take something like, take x minus y, say being purely time, right? I could take something like that. Just some space-time separation between me at the origin right now and me at the origin some amount of time later. That's a fine time-like separation. So in that case, so this is 2 continued. Right, if we were putting in something that only had the time part, we only get the energy part, which if I'm in that rest frame is going to be somewhere else, right? If I go to my rest frame, right, the only part that's going to survive is with mass. So for time-like separations, this thing is going to be going like e to the minus I and t minus the positive I and t to something non-zero. Basically, it's like some sign of m t. The only thing that's going to determine the time dependence will be the mass. That's the only thing that will matter in that frame. So that shouldn't surprise us. And again, that's a C number. So the details of it don't matter right now. I'm just saying it's some number. We can calculate it's non-zero. But importantly, it will vanish for space-like separation. do something like x minus y squared have just be equal to something purely space-like. These are vectors. We take that as our space-time separation. Now when we look at the commutator, which is this delta. Right, this will be at the same time, right? Over here we're separating out the spatial and time part. This is where we're saying, right, they're evaluated at exactly the same instant. The only thing separating them is space. So we have a 2, we have a e, which we know what it is. It's square root of, when we pull out the 1/2 from below, this would be d3p, 2 pi cubed, 1 over square root of p squared m squared, e to the I p dot x minus y, and minus I dot x minus y. Those are real 3 vectors now. Right. But notice sort of the funny thing. So it's not obvious staring at this. Or is it? Is it obvious that this is 0? What?
Because it's that integral of that e to the I overall space is a delta function, and we know x minus y is not 0.
Oh yeah, right. So that's another. What I was gonna. So you mean for this piece? This
Yeah.
piece by itself is delta minus.
Yeah, delta of x minus y.
Right. And then what's this?
I guess also delta of negative x minus y.
Delta of what?
Y minus x, I guess.
So it's actually.
Where's that?
Let me see. If we can, I guess actually you can think of it like that. And then. But then it doesn't vanish, right? Or does it obviously vanish? Because then you have 2 different delta functions.
But aren't they both 0 individually? Or
Sorry. you're
because we
saying-
know x minus y is not
Oh,
0.
Wait, sorry. No, it's not a delta function, is it actually?
The integral over all space of p.
But because of this thing, it's not, right?
Oh yeah. Sorry.
Yeah, yeah.
Yep, you're right.
Okay, so sorry. Another way to see it, I thought maybe there probably is more ways to see that it's 0. But one way to see that it's 0 is, let me think of these 2 terms as 2 separate integrals that I'm adding together. I could do that, right? I could rewrite this as integral with the positive sign minus integral with the negative sign, and call the dummy variable in that case something else if I want, right? Moreover, I could flip the sign of that guy because this is secretly p squared dp, so changing p squared doesn't change anything. Changing p squared doesn't change anything to minus p, changing p to minus p doesn't change because things depend only on p squared, right? So you can see that flipping the sign, so this is 0, since one can flip the sign on the exponent. Exponent. And if it's 0, so you could sort of reason backwards in a way. If this is 0 for this particular type of space-like separation, we already know that the way we've defined delta is it depends only on the space-time separation. So although we've only looked at one space-like value, because the overall function depends only on the space-time invariant, this is going to be 0 for all possible space-like separations, which is very good, right? So that ensures, at the very least, that this is minimally probable. So, and further, delta, I almost called it. So, for all space-like separation. So right, there's another, this is actually related to the propagator. I called it the propagator, it's not technically the propagator. But we could have addressed our question of causality in a different way. Maybe a sort of more physical way in a sense. I mean, we started out with this sort of somewhat formal requirement, right? We want some commutator stuff to be zero outside the light cone for us to be okay with causality. Another thing we could ask is basically what's going to be the amplitude of, to find the field, some position y, if we know what the field value is at some position x. See how well correlated those things are, and look at different space-time separations for them. So, are there any questions, by the way? Sorry about this. Hopefully I wasn't too fast or anything. So another approach to causality we could say you prepare some particle at some space-time point at y, and ask for the amplitude defined at x. Amplitude at x. So the way we would calculate that is looking for some overlap. Right? We haven't actually calculated things like that before, but it's sort of like an expectation value. So it would be this sort of object. So we remember, right, we were convinced ourselves when the field is acting on the vacuum, this is basically creating a particle at some space-time point y. So we can think about causality in another way by looking at what this object is. This basically, this is actually what we mean by the propagator. This will tell us, right, if I know something about the field value at y, what's the field value going to be at some other x, right? So it's a generalization of what we were thinking of propagators before, right? Before, propagators were strictly in the time sense. This is now a souped up version that only depends on space-time. So right, we can put in all our information about do our same expansion. We actually start over on farther over, so we don't run out of space. We could write this as 3dp 6. Let me just do that. 2 pi cubed twice, and square root of 2d to e prime, and we'll have this only part that will matter, the AP prime dagger, because anytime I have a AP acting on 0, right, that's 0. So for this whole thing to be non-zero, the only terms that will matter will be the ones where AP dagger, something dagger comes first, right? Times your minus I tx plus I t prime y. And this actually is a familiar object too. Remember, we found ultimately what the creation operators were doing, but it's creating a momentum eigenstate, right? We defined this thing as a momentum eigenstate. And moreover, we knew we were very careful about what's the proper inner product for two momentum eigenstates. And we found that this is really E prime, inner product of E prime, which is equal to 2 pi cubed delta cubed p minus d prime. simplifies a lot. D 3p, 1 over 2 pi cubed. Some of the 2 pi's will cancel, of course, that's part of the point of having that definition. And 1 over 2 ep, e to the minus I, t dot x minus y. But this actually is the form of the propagator we'll use more often. And so this thing is so important it gets its own shorthand also. We call it d of the space-time separation x minus y. And we'll call it the propagator. We could see also that this is related to our commutator. So another important fact. So it makes sense physically, right, just to connect. So I started out with my concerns about causality, right? First formulate it in terms of a commutator, now formulate it in terms of a propagator, but I can rewrite the commutator in terms of propagators. So you could check. Actually, it's not so hard to see just from this expression, and one of the ones we wrote down before for the commutator, right, that it was a difference of some exponentials. So you could show, right, that commutator of phi of x and commutator of phi y is just equal to d x minus y minus d y minus x. Just flip the sign. So things are fitting together, right? No matter how you want to think about causality, you're led to the same sorts of objects. Which are built up out of, ultimately, things having to do with this D operator that we call the propagator. So, right, now we're finally, this is actually probably the most important, one of the most important results we'll get to this chapter, and also why we had that detour with contour integrals. Because we're going to use this result over and over again, right? It sounds pretty important, right? It tells you how to deal with propagation in quantum field theory. So the one we ultimately actually end up using is not exactly this propagator, but a related friend of his called the Feynman propagator. So some definitions, and then we'll actually show a nicer way to rewrite the Feynman propagator using a contour integral. So this is a very important object. Quantum field theory. So we write it the same way we were writing our commutator before, but with an F for Feynman. And this is really, I have to define a few things actually to write down what it is. So we often write this as with a T in front of phi of x, phi of y. The T is to be defined in just a minute. But what it stands for, you can get from what I'm writing right now, which is that it's going to be equal to the ordinary propagator in the case that the time given by, right, these superscripts, right, mean time, right? So if the time associated with x occurs after the time associated with y, then it's just given by d of x minus y, and the opposite condition. And this thing, T, is called time ordering, right? Which obviously means what you could infer. A short way to remember it, though, is so this T thing, right, this time ordering, we'll have other sorts of ordering. We have to be very careful with quantum field theory. But right, so we're just defining a basic You could also define this in terms of theta functions, right? If you want to have it being, it abruptly changes to some other definition, right? When you flip the sign, or flip the order, rather, of x naught and y naught. Right. Short way to remember is that later means to the left. To the left. So that seems kind of funny and formal. And we'll actually basically never use this definition of it. It's just a way for us to start connecting things, and then we'll find a much better expression that will be easy to remember. And you'll use it so often, you'll never have to memorize anything. It'll just happen. Okay, so this is some related thing. It reduces to our other propagator. I mean, it's equal to our other propagators in different limits. For the propagator we just defined, right? And there's a nice way to summarize that. That's not at all obvious at first, but we'll go through to show why it is. So let me write a claim, and then we'll try to justify it. So there's a very useful way to rewrite the Feynman propagator. So these are just definitions, right? It's a little definitions on top of definitions. But we're going to come back to time ordering and things like that. So they're helpful to start thinking about now. But there's a good way to rewrite this delta f in terms of a 4D integral, in terms of some d4 dp, and also something that's explicitly Lorentz invariant. So let me just write it down, and then we'll show that it's the same thing secretly. And there are some other subtleties associated with it. So it's d4p over 2 pi to the fourth I p squared minus m squared e to the minus I p divided into x minus y. So everything's definitely Lorentz invariant, right? By this I mean p mu, or p squared, right? So at first, right, this probably seems also scary, in addition to not being obviously connected with the same name. I mean, I'm calling it delta f, claiming that they're actually the same thing. But why should this be scary, by the way? I mean, p squared is supposed to be equal to m squared, right? Remember our relativistic kinematics? The nice thing about, so denominator looks very wrong. Since, right, what do I mean by p mu? My p squared, right, is supposed to be p mu, so p naught squared minus the momentum, right? Which is supposed to just be equal to m squared, right? So this is now sort of a subtlety which the book sort of glosses over. We're not going to spend a whole lot of time about it, but now this is the first time where we're going to allow for this condition to not always be imposed. Now, p0 will be a variable that we integrate over. So when you do this, we're no longer going to require that p naught be equal to EP. By EP, I really mean the energy associated with momentum p. So this thing, yeah, I'm trying to think about the notation, but I guess this is the best notation there is. So we're no longer going to require this condition. sometimes called the or on mass shell, I guess. Sometimes you may have already heard that in papers or something, or in talks. Whenever you have this condition really being equal, that p squared is equal to m squared, and that p naught is equal to p, people call that the on mass shell condition because secretly, well, not secretly, but I mean, right? You could write down the geometry basically of what is, you have three other momentum to worry about here, but I can only draw for two of them. If you were to write down what the condition that we usually impose, which is that we usually have e squared is p squared plus m squared, have some hyperboloid something. Well, how do I get a picture? So this is something called the mass hyperboloid. So right, when we require this, the other name for this thing is requiring that you lie really on that mass shell. But basically because of quantum mechanics, and this is a way to make sense of what we're doing, because what we're going to allow is that p naught be some variable we integrate over. It doesn't have to be fixed to be that condition. And what those correspond to, once they're off mass shell, are virtual particles. These on mass shell particles really correspond to classical particles. Off mass shell corresponds to things that people call virtual particles, which don't necessarily satisfy p squared equals m squared. Because if you have the hand-wavy way to think about it is, this is okay to allow excitations that exist for a little bit because because of Heisenberg's uncertainty principle, right? You could steal a little bit of energy for a short amount of time and violate the condition that we usually impose for kinematics. But we'll see, not today, but we'll see eventually that although we have to incorporate that for consistency in quantum mechanics, this off-shell stuff, most of the time, all of your physical amplitudes are going to be dominated by things that are very close to satisfying this classical on-mass shell condition. But it's now no longer a requirement. So that's the first time we see that, which can be confusing. There's also, right, connect to with our stuff about contour integrals. Right, this thing has poles now, which suggests a way of dealing with, of evaluating it. Right. So as written, right, this expression is ill-defined. Needs some prescription for dealing with poles. Since there are poles. And a lot of them actually, right? For each momentum, there's a new pole to worry about. So when P naught hits plus or minus EP, and right again, EP at between P squared plus M squared, right? Someone gives you momentum, you can calculate at least the sign for what the total energy is. But things start to blow up when our variable, P naught, which we could think of as some dummy variable in our integral, and that thing hits sort of the on mass shell energies, the ones given by the normal kinematic relation, there's an explosion in the integrand. So we need a prescription to avoid the singularities. So to evaluate basically this, the P naught integral, right? The way we wrote delta F before was all these three integrals. So the way to connect to show that this is actually the same thing as what we had before we need to do the d0 interval, dp0. To evaluate the p naught interval, we need a description of the poles. So I'll draw the one that's associated with the Feynman propagator. So let's say this is the imaginary part, this is the real part. So I'm already, by the way, jumping to the way that we're going to do this, right? I'm going to use our complex contour integral trick, which means I promote the zero part of momentum, time component momentum, to some complex variable. So now he's not confined to be just on the real axis. At the end of the day, though, that's the axis I care about. I don't care about stuff that's imaginary momentum. So I'll have two poles, right? One at minus EP and one at plus EP. And the one that we need to evaluate for the Feynman propagator is this. We avoid both poles, but in opposite directions. So you're not expected to guess that, but you can, there's only 4 possible choices, right? I could go up and then down, that's another one. I could go down twice, or I could go up twice. Right? So there are 4 possible choices. All 4 are something interesting, actually. It just turns out that this choice is the most, is the one that's relevant for the Feynman propagator. So now let's check that claim. Check the claim that this actually is the same thing as what we wrote before. We need to evaluate that integral. So, a non-proof proof. Right, let's look at our t squared minus m squared thing. So, right, again, this is a full 4-dimensional shorthand, right? So, if I expand that out, this is really p naught squared minus p vector squared minus m squared, which I could write as p naught squared minus EP. Right, just using the EP is just that thing, right? Squared. So you encountered actually really similar integrals, so this shouldn't be too hard for us to do. So I can factorize this thing, right? As P naught, I don't even need the parentheses when I'm doing, but P naught plus EP, P naught minus EP. Writing everything upstairs. So right, there's another ambiguity. On top of the ambiguity of which way you go around the poles, is which way do I close the contour? Right, so our usual way of doing this is I want to close the contour and choose the right way of closing it so that the upper or lower part will be 0. So, which plane do we choose? There's a clue, sort of, and given that we already know by the definition of the Feynman propagator, he depends on which one was first, y or x, right? So the choice for which way you close also depends on the same thing. So for x naught being greater than y naught, say, what we'll have is the delta f will look like something like pt naught. If I go with the large just writing it indirectly. Right? Schematically, we're going to have something like that. There's some prefactors in front too, but let me just focus on the exponential part, right? So, right, I want this thing to become 0, right? What's the way to do that?
Make it space-like?
What's that?
Make it space-like?
Well, here I'm fixing the choice about the sign,
Oh.
right? So I'm saying this thing in the exponential, that part's
Oh,
positive.
just make that really big.
Yeah, exactly. I want it big and also negative, or also imaginary, right?
Yeah.
So which direction do I have to go? Which plane? For that to be true. Do you see what I'm saying? So I just want, for this thing to be 0, as P naught becomes very large, this is basically the way you choose to go to the bottom or to the top in closing the contour. Because I want to forget about that thing. So what do? If I choose this to be negative, right? This will become minus overall, right? So I'll have minus minus, but I squared. Or sorry, yeah, right. So for P naught going to minus I, imaginary infinity, right? This thing will become damped, so meaning I should choose the lower half plane. This is the crucial way that you decide, right? If this was flipped, remember the Feynman propagator depends on the order by its definition, right? So if I flip that, then this now is instead a negative number. So I should choose the other. I should choose the upper half plane in the other case, right? So, and what was our trick for using that Cauchy integral theorem? So does anyone remember what that was?
Well, the pole that you enclose will contribute 2 pi I times the residue.
Yeah. So the whole contour, I think we were writing it like this, right? If I want to evaluate the total contour, total closed contour of something that has the form of f minus c over z minus z naught, and z naught's a pole, that's equal to 2 pi I f z naught, right? So we just argued that this thing on the left-hand side consists of the thing we're interested in, the real axis part, and something that's 0, right? Right. So all that we're really interested in then is what's the value of the function, the integrand, minus this part that diverges, evaluated at z naught. So we'll need to evaluate, this thing is also called the residue. Instead of z naught, right, we're going to be evaluating the integrand, which I'll just write as f, at p naught equals positive, right, this is the other important thing. Right, if I go now for the lower half plane, so this is what I'm going to do for the first choice. Then the only one that's inside my contour is the positive one, right? So that's the thing I need to know the value of. So we don't have, unfortunately, the whole integral written down, but I guess you have it in your notes. So remember too, right, we're separating out the part that diverges, so this is the only part I have left over. P naught plus EP. So that's in the denominator. And I have the exponential, right? Which is, I'll separate out the space and time parts. And then plus I P vector minus y. I want to evaluate this whole thing at P naught equals plus EP. Right? This will be the residue, this will be the part that's relevant, that's non-zero for the rest to evaluate the whole thing. Right. Another important subtlety was that the normal definition for the sign was that this is for counterclockwise contours. There are a few signs you need to worry about, but this guy is not counterclockwise, right? This is clockwise. So for us, we secretly have a minus sign there. So our, we actually write now important stuff. I'll rewrite the thing started with, the claim, which was that if I have d4p over 2 pi to the fourth times I over p squared minus n squared e to the minus I p x minus y. I'm not going to touch the d3 integral, because that part's in the definition of the Feynman propagator anyway, right? So I'll have d3p, and I'm replacing, I'm going to now use Cauchy's theorem, right? Now I can replace the d0, the p0 integral with minus 2 pi I times this thing evaluated at p over p naught. So p naught equals EP. And when p naught is equal to EP, what that first term would become is 2EP, right? This becomes e to the minus EP, x naught minus y naught, plus I p divided into x minus y. So that's an important step because that's almost the final result. It's almost what the Feynman propagator was defined as. Right? It's in the right form now. Having an integral only on d3p. Is it clear what we're doing in this step? Maybe too many things at one step. So now we're really just applying Cauchy's theorem just to that one part of the integral. And what we find is, thankfully, we'll have a 2 pi that's going to cancel. And, oh yeah. There's one thing I'm confused about. Oh, right. Sorry, I forgot another I, right? So, the way that, what I want to do really is insert now our information about what the residue is in terms of the function we define as the Feynman propagator. So, right before we were focusing on all the stuff having to do with the poles and all that, but there's actually an I here too, overall. Which is why we crucially need to worry about that minus sign, right? We did the contour going clockwise rather than counterclockwise, because now the dust settles, the 2 pi cancels one of those 2 pi's, so now we have a d3p over 2 pi cubed with the right normalization over 2ep. And I times minus I is plus, so we get finally, right, that this, the thing we started out with d4p minus I p minus y, that's really just equal to this thing, d3p, 2 pi cubed, 1 over 2 EP, e to the minus I, b x minus y, which is d of x minus y, like it's supposed to be for the choice that x comes first, or sorry, x comes second, that x naught is greater than y naught, right? So let me just write down quickly how you could do it the other case. For y naught greater than x naught, close the contour in the upper half plane. Same choice, we still avoid the poles the same way. In the upper half plane. And because you do that, now you're going overall altogether counterclockwise. So as a result, I'll just write down some of the steps, not all of them. Then the Feynman propagator, the D4 one, we'll have basically applying the same final step. Instead of there being minus 2IP over positive 2EP, it's going to be positive 2I over minus 2EP. Just because now the only contour we're enclosing, remember what it looks like was we first go down and then up. So before we were encompassing only this pole, now we're encompassing only this pole, which has the value P naught minus EP. So that's where we get this minus sign in that case. And the exponential is e to the IP. It's not minus y naught plus IP x minus y vectors, which finally you can rewrite as d3p over 2i cubed over 2p y minus x, which is d of y minus x. So you do have to worry about those minus signs to get the right expression, that the Feynman propagator will be depending only on x minus y, or will be, this function b depends on x minus y if x naught is greater than y naught, and the opposite if y naught is greater. So there's another quick way, instead of just having to remember the right order for things, is a simple way to write down what the D4 integral is. See what you remember. You can write Feynman propagator. Just with, this is called the I epsilon restriction, obvious reasons. Still have the same I, d to the I, d f, p minus y, over p squared minus m squared plus I epsilon, for epsilon being positive. Right, this is called, we can see why that's the equivalent. Right, so if I do this now, what do my poles look like? So now, with this being the case, I have poles at P naught is plus minus EP minus I epsilon, right? So what that would look like in the imaginary plane is that now I don't need to worry about it because now my contour can just be this along the real axis because now I've raised one pole up to I epsilon off and raised this one down minus I epsilon. So that's other simple ways to remember for the Feynman propagator how you do that. So we'll see actually right away why this thing is useful, possibly even for classical field theory, why this object is useful. Remember, we have a funny condition that's very non-classical. We're allowing P naught to be just a variable. It's not fixed by the normal relativistic kinematic requirement. There's another reason why you might study something like this even in classical field theory. And you certainly did, I guess, when you one class you had a classical field theory with electrodynamics. Probably did encounter objects very similar to this, because these are related to things called Green's functions. Any questions about the I epsilon prescription? This is just like a short way of reformulating the same thing. So, right, another useful application of the Feynman propagator, or of propagators. There are other ones. I'll say a little bit about them. Basically, you get different types of propagators by closing the contour in different ways. Right? If we didn't do this I epsilon thing, we could have gone up twice or down twice. So those choices correspond to two other types of propagators that are useful in classical field theory, but not as much for quantum field theory. So the other important application is that, so it's a Green's function for the Klein-Gordon operator. You don't need to worry about contours or anything to show that. So, right, we can just look at it right away. What is the Klein-Gordon operator? Is the thing in the Klein-Gordon equation that acts on phi. So the Klein-Gordon operator is this. Right? If I have that thing acting on phi, that's supposed to be 0. So I claim if we act on the Feynman propagator with the Klein-Gordon operator, take the Feynman propagator and act on it with this operator, we should get some delta function, indicating we have a Green's function for that operator. So let's do that. Right, what's nice is the way we wrote the Feynman propagator, right, has everything in terms of P and X very explicitly. So I know how to carry out these derivatives. Right, so I have d4p over 2 pi to the 4th, pi over p squared minus m squared. So first thing, right, if I'm taking 2 time derivatives, right, I'm going to bring down p naught twice, minus p naught squared. and I have a overall minus sign in front of the spatial derivative. But again, I bring down now two momenta which will be dotted into each other and squared, and the mass term is the same. It doesn't do anything. EIP dotted into x minus y. So this looks like, so this will be minus energy minus momentum, which I claim should be this. Is that right? So, right? Because right, now they have the same sign, right? Wait, no, there is something wrong.
That seems right. Oh. Oh no, that doesn't seem right.
So if I'm doing the derivative, this should bring down minus IP, so plus, and minus, actually, right. So actually it is minus with a minus, isn't it? Right? Does that make sense? Because I get overall a minus from the I times I. Who cares about that minus because he's squared, right? But the I times I gives me a minus, which with this other minus gives me a plus, right? So now, I'd like to have the minus sign on him. That's the way I defined for momenta inner products and stuff, right? We chose the weird sign, which is to have 3 wrong signs rather than 1, but that's what we chose. So really this is minus p squared in my shorthand for vector notation. And the m squared is the m squared. So nicely this will cancel this p squared minus m squared. It will give me a minus 1 overall. So I have a minus I can pull out. d4p over 2 pi to the 4th e to the minus I p x minus y. So this now we could use the nice formula that we were almost going to use earlier, which is right, the Fourier transform of a delta function is an exponential. So in other words, this thing is all equal to just some delta function. Minus I has a funny number in front of it, but it's a 4-dimensional delta function. And we didn't need to say anything about the contour to get that result. So you can see why you might encounter this thing in classical field theory, right? Classical field theory, you have to worry a lot of times about choosing the right contour and all that. Or sorry, you have to worry about Green's functions. You don't usually have to worry about choosing the right contour. Right, so let me just say, we won't need to use this, but for completeness, since it's a natural question. So, some purposes, the are helpful sometimes. So, the one where we go over minus EP and plus EP. That guy's called the retarded contour, or because it's related to the retarded Green's function. And then the one where you go both under, minus EP plus EP. And guess that one's called the advanced. So for example, the retarded propagator is 0, why not bigger than x0? And if it's not, it's given by the difference between d of x minus y and y minus x. So right, the situation where this thing could be helpful are when you know some initial field value and you want to know what will that look like in some later time. How it'll evolve basically in the presence of a source. So these things is delta R and the equivalent one, the advanced propagator, delta A. So a couple ones studying, we're not going to do this now. The book has a very short intro into it that is not really relevant. But these are useful when you're studying a classical source. So, for example, when you have instead of the normal Klein Gordon equation, which would be equal to 0, and this is that same Klein Gordon operator I just wrote, right? Ordinarily, we say this is equal to 0. But if I have some source, a sink or something, whatever, something that's spewing out, say, phi particles, just by some prescription, and I mean that just in a classical sense, right, then I can think of trying to evaluate the dynamics of this classical scalar field in the presence of that source, and knowing what the source is at some time will allow you to figure out what it is at some later time using this retarded propagator. Right. So this sometimes is helpful. Right? So this is, if we wanted to, right, we could start studying interactions in this very simplified and strictly classical way. But instead, what we're going to do, and which lets you get to Feynman diagrams, I think the fastest route, is next time we're going to start in on chapter 4. We can skip over chapter 3 for now. We're not abandoning chapter 3. The world is mostly fermions, after all, so we have to worry about fermions, which is chapter 3. But to get us start thinking about Feynman diagrams and that formalism, I want to jump into chapter 4 right now. And then we'll return to chapter 3. And then finally combine them, right? So the goal after that will be how do we start thinking about some elementary things that can happen in quantum electrodynamics. So that's where we'll use Feynman diagrams, but now to tell us how interactions work between fermions. And that's also a real physical theory, right? It's not a toy theory. It's the one that actually describes how charged particles work in a quantum mechanical and relativistic way. So I don't think we're too far from that. So next lecture we'll start in on probably the most important chapter, this semester, which is chapter 4. So we'll be able to start calculating some real things there too, things like cross sections and decay rates. So practical things in the end. All right, hopefully that sounds good. And don't forget that there's a homework due on Wednesday. All right, any questions? All right, see you guys on Wednesday.
Can you have my lunch with me?
What's that?
I can eat at my lunch with me.
के छ के भयो यस्तो कति भयो गयो इडली गर के अरे को खेलेको बोलियो
आन्सर गरौँ मैले त्यसो उसमा चाहिँ
जाने हो अनि म त्यो भन्ला लगआउट लगआउट नकआउट
Did you hit your lunch?
Yeah.
Where there isn't a micro over here?
Yeah, it's over. If you go down on the first floor, you go down towards that side of the building.
Side building.
No. So if you go towards that side, and then on the left of the hallway near the end of it, there's like a little area with like a fridge and a microwave and a sink.
Oh, okay. So we'll go down the first floor then on our left side.
Yeah.
Oh, usually I wanted to, you say to hit.
Yeah.
Oh, okay. Next time maybe.
you do the quiz for E&M?
Yeah.
Yeah.
Reading quiz, right?
Yeah.
We should do. Maybe yesterday.
I was kind of upset that he released it yesterday and made it due yesterday.
Me too. I submitted at around 8:30.
I submitted at like 11:28,
11:28.
like 2 minutes before it was due.
Isn't that so? There are two quiz, right? On GTL. One is reading quiz. Is there any? Let me see.
I would assume there's going to be one before class like he usually does. Survey.
Oh. Is it before or just in class?
Yeah, well, yeah, like the one he
In
has
class.
us do in
In
class.
class.
In class at the start of class.
Not two quiz. Okay. So you cook lunch yourself or eat no snack? Chinese food is green pepper and
Broccoli, green pepper,
Broccoli.
onions, and jalapenos.
or the vegetables
And a
mix
little
them
meat.
together.
Yeah. Stir fry.
That's good. Actually, when we are doing quiz, if we took a picture for our equation, then we can't submit, right? I tried yesterday,
Yeah.
but when I click the camera button, it says enter your URL.
Oh.
So it's not a picture. Oh. Oh, yeah. Please.